So welcome to presentation. So here we discuss formulation, material analysis, advanced systems, and configurations. My name is Keisuke Saito. I'm product manager for X-ray diffraction at Rigaku Americas Corporation. Pharmaceutical products in the formulation process are investigated for different parameters depending on form of the product. For freeze-dried product, the sample might be placed under the cooling or heating environment to investigate crystallization or TG and phase transformation, and the environment might be vacuum as well. For samples in tablet or capsule forms, the crystal form of the API, coating materials, and cavities might be the targeted analysis parameters. X-ray powder diffraction is widely used to investigate APIs, excipients like a coating, binder, lubricant materials. Sample form could be powder, tablet, liquid, or gel. Typical applications are polymorph analysis, quantitative analysis, crystallinity, phase identification, microvolume sample, or microspot analysis. We have two XRPD products, SmartLab and SmartLab SE. There are a couple of unique features on the products. First, both instruments support reflection transmission geometries. On the SmartLab system, two different modes are switched automatically without touching anything. On the SmartLab SE system, you can just flip sample stage 90 degree or 180 degree to switch between transmission reflection geometries. Secondly, we have DSC option. DSC, or differential scanning calorimetry, is a thermal analysis equipment. We produce not only X-ray related products, but also thermal analysis products as well, and DSC is one of them. You can have this option for in situ XRD-DSC measurement. Johansson Ka1 is an ideal XRPD configuration for high-resolution measurement. It monochromates X-ray down to Ka1 radiation only. It provides much cleaner diffractogram due to missing Ka2 radiation. It provides better result in application where precise diffraction peak intensities, positions are required. For example, indexing, structure refinement, or structure determination. For high throughput, 610 and 48 sample changers are available for both instruments. SmartLab could have 96 well plate support as an option too. 9 kW high power X-ray source or Photon Max is available for SmartLab. That can accelerate all the measurement by a factor of 6 compared to conventional sealed X-ray tube. These are the high throughput and sample changer solutions. The 96 well plate supports both reflection and transmission geometries. This option can be taken off from diffractometer easily, so you can use it for other applications, including non-ambient in situ experiment with large chamber. 48 sample changer has two cassettes for samples, and each cassette accommodates 24 samples. Robot picks sample from the cassette and drives it to diffractometer. Both reflection and transmission geometries are supported. 10 and 6 sample changers have compact design and can be replaced with any other sample stages. The 6 sample changer is especially designed for reflection and transmission geometries. This slide is showing how reflection and transmission geometries are switched with the 6 sample changer. Samples stay horizontal, but diffractometer rotates 90 degrees to switch the geometries. You can assign the geometry randomly for each samples on the changer. Reflection geometry is generally used if your sample is prepared in an airtight sample holder. It probes more on surface area as the penetration of the X-ray is shallower compared to transmission geometry. However, the drawback is preferred orientation of the sample crystal. As powder sample is pressed onto the sample holder, the sample crystal tends to have strong preferred orientation. By having that, quantitative analysis, structure refinement might have difficulty to get the right answer. Transmission geometry on the right-hand side probes entire sample. This is especially important if you want to evaluate small amount of impurities or polymorphs if they are not distributed uniformly over the sample. This geometry also minimizes preferred orientation, as the sample is not pressed like a reflection geometry. Software integrated with smart labs equips generally requested application and user management capabilities. For example, automated search match for phase identification, peak search, quantification by calibration curve, whole powder pattern fitting, and read felt refinement. This slide is summarizing some of the unique and important features only. You can register user into the software. You may provide different privileges depending on user right. You can define more than 2 user rights, for example, for administrator and for operators. When you register a user, you can provide the user right. We do support ERES audit trail compliant with FDA 21 CFR Part 11, EU GMP Annex 11, and PSES. For analysis, clustering and DD method are supported, as well as the basic applications mentioned before. The DD stands for direct derivation. This method was developed by us and first published in the paper in 2016. This method enables us to quantify crystalline and amorphous materials without the structure information. We will demonstrate some of the features during XRD workshop later today. In situ XRPD measurement is available by combining various chambers or attachments to simulate environment around the sample. The XRD-DSC option is a unique solution from us. The DSC profile are measured simultaneously with the XRD profile. You may control temperature and humidity. By that, you can correlate thermal reactions with crystal structures easier than the separated instruments. TTK 600 on the right-hand side enables to change temperature between -190 and 600 degrees Celsius under vacuum, minimum 0.01 Pascal. This is an ideal temperature vacuum chamber to simulate freeze-drying process. Instrument control software recognizes these options once it is mounted, and sample alignment is automatically carried out. Temperature, XRD, and DSC conditions are fully controlled by the software, and you can program it easily using a graphical user interface of the software. Various sample holders are available too. Low background sample holder is designed for small quantity or physical shape of the samples. Sample holder itself doesn't show any diffraction peak. Therefore, you can over-illuminate your sample. However, absorption correction is necessary for some applications like quantification or structure refinement by a read felt refinement method if X-ray over-illuminates your sample. The tablet sample holder is made for tablet sample as named. You may use this sample holder for both reflection and transmission geometries. Disposable sample holder can also be used for both reflection and transmission geometries. The outer ring is made from a metal, and this part is reused. Inner part of the holder that holds your sample and capsule window is made from a plastic. This part is disposable. We have a couple different designed airtight sample holders available. This one shown here is designed to keep environment inside maximum 48 hours. It can have integrated knife edge inside for 1D or 2D detectors. Low background insert is also available for this specific model. This is showing a bit more details about DSC option. It has two sample holders inside the chamber for reference and your sample. We normally use aluminum or corundum as a reference sample. Your sample quantity will be between 3 and 10 mg of weight. Temperature supported is between -40 up to plus 350 degrees Celsius, and atmosphere could be air, inert gas, nitrogen, or humidity-controlled air. So depending on the required humidity range, the temperature range differs. Scan range for X-ray diffraction will be between 1.5 and 60 degrees to theta. Both temperature and humidity, if equipped, are fully controlled by instrument control software. You can edit the program on the graphical user interface of the software. This is an example of XRD-DSC measured on acyclovir. Environment in this measurement was dry nitrogen. Temperature was elevated from 30 degrees C up to 200 degrees C, then decreased back to 30 degrees C by a constant rate. XRD profiles depending on the temperature are summarized on the left, and DSC profile together with the temperature profile in the middle. Original crystal structure when the measurement started was 2/3 hydrate, which is in green. After a dehydration peak at 93 degrees Celsius, anhydrous form 3 appeared, which is in yellow. This phase was transformed to anhydrous form 4 at 200 degrees C, which is in blue. When temperature was decreased, it became anhydrous form 2, which is in red. The DSC profile showed two peaks for the phase transitions from 2/3 hydrates to form 3 and from form 4 to form 2. However, it is not clear if there is any peak on the DSC profile when the phase transformation happened from form 3 to form 4. However, if you have XRD combined DSC instrument, like this example, it is quite easy to identify the phase transformation happened at 200 degrees Celsius as powder diffraction pattern changed between form 3 and form 4. Crystal structure of form 3 and 4 were not known, or at least there were no databases available for these powder diffraction patterns. To determine the structure, the easiest way is to have a single crystal and analyze it by a single crystal X-ray diffractometer. However, some of the crystal is difficult to be prepared in the single crystal form. Also, in this case, these phases appear only at elevated temperature. Structure determination on unknown or partially known crystal only from X-ray powder diffraction pattern is also possible if you have right tools. To do so, we need to have high quality powder sample without polymorph or impurity phases. And high quality X-ray powder diffraction data and software are necessary too. Assuming you have high quality powder sample, we provide other required conditions. First, to record the high quality XRPD data, we may need to have monochromated X-ray. As you may know, conventional X-ray source generates two different characteristic lines called Ka1 and Ka2. These lines have slightly different energies, means they show two peaks overlap each other. by having these two diffraction peaks for all HKL diffraction peaks from your sample, peaks will have more overlap. This makes structure determination difficult. Johansson K-alpha-1 monochromatometer, which is discussed in next slides, will monochromate the X-ray energy down to pure K-alpha-1. This decreases total number of the peaks to half and also decreases peak overlaps. We must have a software that enables us to do indexing, space group determination, structure modeling, and structure refinement. Our analysis software SmartLab Studio 2 has all the features in one software package. Johansson monochromatometer is a curved single crystal. It is placed between X-ray source and sample. K-alpha-1 radiation from the source is diffracted by the crystal and introduced to the sample. X-ray is kept as a divergent beam for black-plane tunnel reflection geometry, or you could have an optic after the Johansson to shape the X-ray beam to parallel or focusing depending on your application types. As it provides only K-alpha-1 radiation, compared to the conventional K-alpha-1 and K-alpha-2 mixture, number of the diffraction peaks are half and less overlaps between the peaks. The Johansson K-alpha-1 provides high quality data, however, it compromises on measured intensity. On the SmartLab, the Johansson K-alpha-1 can easily be taken off. Please allow me to show you one of our YouTube videos that demonstrates how it works.
Johansson primary beam monochromators play an important role in creating pure K-alpha-1 radiation. This highly monochromatic X-ray beam is useful in a number of applications, including decomposition of complex powder patterns, ab initio structure determination from powders, and crystallite size determination from profile analysis. Coupled with Rigaku's CBO optic system, a number of secondary optics can be selected, allowing a number of experimental setups, including regular focusing mode, transmission focusing mode, and others. In the past, the biggest drawback to using a Johansson monochromator has been the severe limitations that the configuration places on a powder diffractometer. Most diffractometers that are configured to do K-alpha-1 data collection cannot be easily switched to a standard K-alpha-1, K-alpha-2 data collection mode. The subsequent alignment is too difficult to undertake without factory-trained engineers present if the system can be reconfigured at all. Rigaku has solved this problem by incorporating a rotation stage on the incident beam side of the diffractometer. When the goniometer is in the standard K-alpha-1, K-alpha-2 configuration, it looks like a standard SmartLab diffractometer with CBO optics. However, the X-ray source can easily be rotated back, leaving space for the Johansson monochromator. After the monochromator is attached to the stage, the SmartLab auto-alignment software ensures that the system is lined up for data acquisition. Reversing this is easy. Remove the Johansson monochromator housing and rotate the X-ray source back to the standard position. Run Rigaku's exclusive auto-alignment routine, and you can be back to collecting data in K-alpha-1, K-alpha-2 mode. This breakthrough in hardware design means that you never have to dedicate a diffractometer to only K-alpha-1 data collection. When you don't need K-alpha-1, then you no longer have to lose the intensity benefit of K-alpha-1, K-alpha-2 data collection because you don't want to reconfigure the system.
So we place the acyclovir powder used in XRD-DSC measurement into a capillary and heat it up to 210 degrees C to investigate the crystal structure of form 4. So we had HTK 1200N with capillary extension. So by this option, so you can apply heat to the capillary. X-ray was monochromated by Johansson monochrometer and focused onto capillary by combined elliptic curved multilayer mirror placed after Johansson crystal. X-ray transmitted through sample and capillary was recorded by a detector. So XRPD scan here was the data recorded on this capillary sample. So we started from 5 degree 2 theta up to 80 degree 2 theta here. Capillary was continuously spun during measurement to minimize the preferred orientation of the crystal. So crystal structure shown here was refined and found by structure determination package of the SmartLab Studio 2 software. So please let me summarize my talk now. So I demonstrated SmartLab and SmartLab Z are versatile for formulation process in pharmaceutical industries. Sample form could be powder, tablet, and capsule, or even liquid or gel. So we provide different types of sample holders, which includes low background, airtight, disposable. For high throughput applications, so we provide 6, 10, and 48 sample changes, or 96 well plate option available for SmartLab. Ambient wise, so you can decrease or increase the temperature around the sample. You can flow the humidity controlled air into the chamber. And even we have XRD-DSC option. Application wise, so we do support from phase identification to structure determination. Conventional applications like a peak search, quantification by calibration curves, so these applications are supported together with newly developed advanced applications like a DD method. XRD configuration wise, so we do support Bragg-Brentano configuration for refraction geometry and focusing X-ray beam geometry for transmission, and Johansson K-alpha 1 for both refraction and transmission for structure refinement or determination application. Thank you very much for your attention.